All right, so our lab S talks a lot about solubility, so I want to remind you a little bit about solubility. So what I have here are 3 beakers, and the first one we're going to say has our copper chloride in there, and then we have some copper fluoride and some copper hydroxide. And these little squares, or what I attempted to make as a square, maybe more of a, not quite even a rectangle, but whatever shape they are, those are going to be our pieces of solid. And once upon a time we talked about our solubility table, and let me pull up our solubility table, and we would have looked for this copper chloride. Now copper doesn't appear, but chloride does. So here's our chloride right here. And it says it would be insoluble if the cation, the positive ion, was silver, mercury 1, or lead, but it is soluble with any other ion. And what we're looking at is CuCl2. It's our copper 2 chloride. Oops, I don't know how this happened. There we go. So our copper 2 chloride will be soluble. So once upon a time we talked about solubility. What we meant is that it's going to dissolve completely into solution, and that solution, that solvent that we were talking about, is water. So all of these solubility rules refer to aqueous solutions. That is where our solvent is water. So just to give you an idea of what would happen, let's say we took our little crystal here and we dropped it into our beaker. So there's the crystal dropped into the beaker. Now imagine you're giving it enough time to dissolve. You're going to stir it up with your glass stir rod. What will happen is the solid will dissolve, meaning we no longer see this piece of crystal here. And instead, for copper, it does turn the solution blue. And I apologize, I'm not great at coloring in between the lines, but I will give it my best here. So again, we had this piece of copper chloride. It went in, and when it went in, it dissolved completely, and we have this nice blue solution, which is what we would see for our copper chloride. And when that happens, we would call this soluble. So soluble or aqueous. So any questions about that copper chloride? So next up, oops, I clicked something, I apologize. Get out of the way, okay. There we go. All right, so next up I'm gonna jump all the way to the end to where we have our copper hydroxide. Now, once upon a time, we talked about things being insoluble and we labeled them as a solid. So let's go ahead and look for that copper hydroxide. So again, copper is not listed here, but we could find our hydroxide right here. And it says that it would be soluble if its cation, its positive ion, was calcium, strontium, barium, lithium, sodium, calcium, rubidium, cesium, or ammonium. So it's a big list, but it does not include what we have, which is copper. Because it doesn't include that, we are left with it being insoluble. And an insoluble compound does not dissolve in water, and therefore it remains solid. So when we have our copper hydroxide, it will be insoluble. So if we take this little crystal and we dunk this in to the water, we stir it up, we shake it, we do our best, it is still going to be insoluble. We are still going to have a chunk of solid right there. And that's what we mean by insoluble. The solid sits in solution. And that is kind of the opposite of what's happening right over here, where it's completely soluble, it's going to dissolve completely. So right now I just want to compare the image on the left of your screen with the image on the right of your screen. So the left of your screen is soluble, completely dissolving. The right side of your screen is a solid, doesn't dissolve at all. It's going to sit at the bottom as a chunk. So any questions about those two, about the difference between the soluble or aqueous and the insoluble, which we would also refer to as a solid? So next up, I want to look at the one that's in the middle. And it's in the middle physically, and it's also in the middle in terms of what it does. So what I'm going to do is I'm going to take this chunk of solid, and truthfully copper fluoride is kind of a greenish blue, but I decided just to keep color consistency and make them all blue little crystals. So I'm going to dunk this one in, but what we see down here is that it is slightly soluble. So we haven't looked at slightly soluble so far, so I want to talk about what that means. So here's our crystal. Now slightly soluble means what you might expect. Some of it can dissolve. So here, what I'm going to do by erasing it is I'm going to say some of that is dissolving. And when that dissolves, because copper does tend to turn our solutions blue, or in this case a greenish blue, we're going to get a light blue. Now, one of the interesting things about copper, and one of the reasons I chose the copper compound, is that the more copper dissolves, the darker the blue solution. The less dissolves, the lighter the solution. So if we just compare these two right here, what we see on the far left is that when it's soluble, it completely dissolves, and we don't see any pieces of crystal. We see a dark blue solution. When we have something slightly soluble, just like you might expect, some of it dissolves, usually very, very little dissolves, and we can see in the case of a copper a very light blue or light greenish blue solution. And again, by comparing the colors, you really can compare the concentrations, and that's actually a principle that we learned about using the UV Vis. And to Tasso's point, I know it's so much harder to visualize it coming from the video than when you actually do it in class. So if you had actually made those solutions, you would have seen a darkly colored solution moving all the way to a very light colored solution. But again, when you have the light colored solution, it does indicate it's not very concentrated because not as much is dissolved into it. Oops. All right, so here are three conditions. We have our copper chloride, which is soluble, completely dissolves. Copper fluoride, which is slightly soluble, some of it dissolves. And the copper hydroxide, which is insoluble and none of it dissolves. The crystal just sits at the bottom like a rock. So any questions on the difference between these three conditions? So in this lab, we're going to talk about solubility of alcohols. So here, I just want to remind you of your alcohols, and this is actually a great lab because we get to review a bunch of stuff as we're heading towards that final. Good question. Will the slightly soluble eventually dissolve completely? And the answer is no. So our slightly soluble compounds don't have the ability to dissolve completely. So it's something that dissolves in a very, very small quantity, and it will never completely dissolve. Very good question. All right, so again, we're going to be talking about the solubility of alcohols. And so here's just a review slide, something that we saw way back when in chapter 3. And just as a reminder, coming up to the final, you should know your functional groups and our discussion on organic chemicals, our alkanes, alkenes, and alkynes. So here were our alcohols. And alcohols, we said, had an OH group. So that our OH group is connected to some type of a carbon group. And way back when, we called that carbon group the R group, and that's very common in organic chemistry. But I also gave you another way to remember R, and I said R is like the rest of your molecule. So this right here was the business end of your alcohol, and this over here is your R group. And we have lots of different alcohols, and let me straighten up that R a little bit. We have lots of different types of alcohols. So here we have methanol. So you might remember meth from way back when in chemistry class, not outside of chemistry class. Meth meant 1 carbon. Now here we have hexanol. Hex meant 6. So still an alcohol, but here we have 1, 2, 3, 4, 5, 6 carbons. So I didn't ask you to know the naming convention for alcohols, but I did teach you about the prefixes where meth meant 1 carbon, eth meant 2, and so on. So just reviewing that a little bit with you. So any questions here about this idea of the alcohol? So there's lots of different alcohols depending on how many carbons are attached. All right, so just again as just a little review, once upon a time we talked about a molecule that looked like so. And by the way, I'm drawing in that skeleton format right here. Is this an alcohol? It's got an OH on it. All right, so I'm seeing a no. So why not? Why isn't this an alcohol? Why can't we call this an alcohol? It does have an OH. Anybody notice something in here that shouldn't be there if it's an alcohol? The double bond O, excellent. So that double bond O we call the carbonyl. This little guy right here, that cannot be there if it is an alcohol. So again, just as a bit of review for us, this is called the carboxylic acid. And by the way, all of these notes are going to get posted to Canvas as soon as I'm done, so you don't have to worry about getting everything down right now. But again, this is just a little review that if it had a double bond O next to the OH, we cannot call it an alcohol. Instead, we call it a carboxylic acid, and it has very different properties. So in this lab, we're going to talk about alcohols only, so there won't be anything that looks like this in this lab. So questions on anything here about why we could say this is not an alcohol? Okay. So here's another review slide, and I just added a few things to it. So back in our last chapter, we talked about colloids and a specific type called the micelle. So what we said about the micelles is this is actually in your soap, and there's something interesting about these individual molecules. And I'm going to zoom in because I know the slide's very busy there. So we have what we call a hydrophilic and a hydrophobic group. So phobic, and I know the font isn't very clear now that I've zoomed in, I apologize. Phobic means to fear. So hydrophobic groups are afraid of the water. They do not mix well with the water, and that is because they are nonpolar. And that is this right over here that's colored in green. So that zigzag there is a carbon group. It is a nonpolar group, and it wants nothing at all to do with the water. Then we have a hydrophilic group. And philic is love. So this is a water-loving group. And what loves water are polar groups. So this is going to be polar. And a lot of times your hydrophilic group is an OH group. It is an alcohol group. And so we saw this in our micelle, and we also talked about how molecules like this are in the bilipid layer that you might see in your biology class. And what we said is when these molecules get together, they hide those carbon tails on the inside, and they expose the polar groups to the outside because the tails do not want anything to do with the water, only the polar heads do. And what I've done up above them is I've compared them with our alcohols. So alcohols are very, very similar to these. So here in green you have, and let me actually zoom in just so we can focus on these right here. In green we have our carbon tail, and we do often refer to it as a carbon tail. It is nonpolar. It wants nothing at all to do with the water. And then we have an OH, and that OH is polar. It is hydrophilic, and it would love to be in the water. So here's the problem that we have, and what we're going to be looking at in this lab, is that we have a molecule that has two parts essentially, and you can think of it as two warring parts. So one part is like, oh my God, I hate the water, I'm terrified of it, don't take me near the water. And that's the part that's going to act or try to act more like oil. It's going to try to get away from that water. And then we have the OH part, which is like, hey, no, water's cool, let's go swimming. And it's trying to drag the rest of the molecule into the water. And so within this one molecule, you have these two pieces, one that wants to be with the water, one that does not. Now we know that sometimes they can form micelles where they just tuck their tails in and then everything's good in the world. But what we're going to find with the molecules we're going to look at today is they don't really have that ability to tuck their tail in and to make these nice round micelles. So they have to kind of decide which force is going to be stronger, the hydrophobic or the hydrophilic. So are they more afraid of the water, or are they more interested in dissolving into the water? And that way we will be able to find out, is this going to be soluble in water or insoluble in water? Okay, so I know this is a really busy slide here, but any questions on anything here so far? All right, so I'm going to take you back again to a slide we looked at last chapter, and this was like dissolves like. So what we found with oil and water is they don't mix. You can take it and you can shake it, shake it, shake it, but the second you stop shaking it, they will separate out. And the reason is based on those intermolecular forces. So oil is nonpolar while water is polar. Water would much rather be next to another water molecule because it has hydrogen bonding. So hydrogen bonding is extremely strong, and what I told you in class is that it really will kind of elbow and shove that oil out of the way so that it can hydrogen bond with another water molecule. So water has those strong hydrogen bonds. So what we would find is if we had something nonpolar, it would dissolve very well into our oil layer. If we had something polar, it would dissolve very well into the water aqueous layer. And also something ionic would go very well into the water layer. And so I drew a little cartoon, again, not a great drawer, but here's an alcohol off to the side here. And it's saying, well, what about me? Where do I belong? Do I belong with the oil or do I belong with the water? And that's actually what we're doing with our lab today, is we're kind of figuring out, where do these alcohols belong? Where do they fit the best? So any questions about what we're talking about here, where our alcohols have two different parts? They have a part that wants to be with the oil, a part that wants to be with the water, and we're trying to figure out where they belong, so to speak, where they will be their happiest, where they're going to dissolve. Okay. So just another comment on the solubilities of the alcohols in water. Here it says the longer the carbon tail, the less soluble it is in water. So I'm going to start by zooming into our methanol right here. So again, meth means one carbon. So here is our methanol with the one carbon. It is very soluble in water. So we have one carbon group and we have the OH group. Next up, we're moving on to butanol. But meaning four. So 1, 2, 3, 4 carbons. It is now slightly soluble in water. So between methanol and butanol, what we see is the tail is starting to grow. As the tail grows, the effect of the hydrophobic part, the part that does not want to be in the water, is more important. So essentially, the larger that tail is, the less likely it's going to get into the water. Next up, we have our octanol. So oct means 8. All right, so oct means 8. So 1, 2, 3, 4, 5, 6, 7, 8. By the time your tail has 8 carbons, it is now very insoluble in water. So again, the longer this carbon tail is, the less soluble it is in water. Methanol can go into water very easily. Octanol, absolutely not. So any questions on anything here? All right, so here is a table of alcohols, and one idea that I want to introduce is the idea of miscibility So we often refer to miscible as having an infinity sign, and that's the infinity sign you're going to see right over here. And that infinity sign means it is soluble in any quantity. Once upon a time, we looked at solubility and we talked about something that is saturated, supersaturated, and unsaturated. If it is miscible, those labels no longer apply because you can add as much or as little as you want. So miscible mixes perfectly in any ratio. So methanol, ethanol, and propanol have this. Ethanol is actually your drinking alcohol, so this one right here. So for those of you over 21, you're welcome to do an experiment, or if you're under 21, with the supervision of your parents or some adult, you can do an experiment and you can try mixing ethanol with water. Any alcoholic beverage has ethanol. That is our only type of drinking alcohol. Any other type of alcohol would cause you damage. So sadly, sometimes someone who's an alcoholic who cannot get standard drinking alcohol will use one of these other ones. So isopropanol is rubbing alcohol, and what you may have heard is that they do add a kind of a poison in there so that it's not meant to be drank. But if you're an alcoholic, it will satisfy that feeling that you have. But unfortunately, it also causes blindness. So one of the big problems that they have in kind of dry areas, which are areas especially on Native American reservations where they don't allow alcohol because they have such a big problem with alcoholism, is that they cannot get ethanol, but they can get isopropanol, your rubbing alcohol. They can also get the alcohol in a mouthwash like Scope, and they do drink it, and again, it fills that urge they have as an alcoholic, but it causes all sorts of internal damage. So all of that is just to say that the only drinking alcohol that we have is ethanol. Anything that says it's alcoholic is definitely, anything that's meant to be drank, I should say, any alcoholic beverage always contains ethanol. So ethanol can be mixed with water in any proportion. So you could take a teaspoon of it and mix it with 2 gallons of water. It'll mix perfectly. On the other hand, you could take 2 gallons of alcohol and put 1 teaspoon of water in it. It will mix perfectly. So any proportions you want. So if it is miscible, this idea of saturated, unsaturated, supersaturated no longer apply because it just mixes perfectly no matter how you want to mix them. All right, so any questions on that idea of miscibility? All right, so what I want to show you here is the increasing of these carbon tails. So here we've got just 1 carbon, that's why we call it methanol. Here's a 2 carbon chain, and there we get that prefix F we've talked about. So F means 2, pro means 3, and here we go 1, 2, 3 carbons. Bute means 4, so 1, 2, 3, 4. Pent is 5, 1, 2, 3, 4, 5. Hex is 6, 1, 2, 3, 4, 5, 6. And here we have hept, which is 7, 1, 2, 3, 4, 5, 6, 7. So again, it's a great lab because I get to review so much stuff with you. Ethanol, yes, ethanol can also be used as a fuel, definitely. All right. So what we see in the beginning is we have our methanol, ethanol, and propanol. All of them mix perfectly with water. And that's why they do so well in propanol as something that we use for our rubbing alcohol, for cleaning cuts, ethanol as drinking alcohol. The ones below it, their tail is too large. Their tail does not allow them to dissolve into water well. So over here, these are definitely not miscible. So the first one, the butanol at 0.11 moles can go into 100 grams of water. It's about 100 milliliters of water. So that is not very much, but by the time we get down to our heptanol, notice we're at 0.0008, extremely small amounts of heptanol. So small that we would probably say it is basically insoluble. So what I wanted to show you here on this PowerPoint slide, in addition to reviewing your prefixes with you, was just that the longer the tail is, the less soluble it will be in water. All right, so questions on anything so far? All right, so now we're looking at solubilities of liquids and specifically alcohol. So these alcohols that we're looking at are going to be liquids. I should say there was one here that was not a liquid. Actually, I'm not sure methanol. No, I take that back. Methanol can be a liquid as well. So all of these are liquids. The reason we don't use methanol too often, well, I should say we use it when we want to, and that is because it's very, very flammable. So sometimes when we're doing demos, it actually is a great liquid to use because you could really light something up well with it, but it is a very dangerous one. But the other ones are safe to use in the lab, and that's why in this lab we wouldn't give you methanol. I know, boo. So it is actually a lot of fun to light it up and see the big blue flames. Anyhow, so here what we're doing is we're mixing equal quantities of alcohol, water, and food coloring. So I'm going to show you here, then we're going to take a look at a video of it. And the first one that I'm going to look at is right down here where it says soluble. So soluble means the same kind of soluble we looked at before. So let me go all the way back here. So here was the soluble solid. When you put in that crystal, it dissolved completely. There was no trace of the crystal left. That's what we're talking about. But now we're talking about it with a liquid. So if you were to do this, first thing is we're going to put water with food coloring in there. So I'm going to color the water. That way we know where it is. Oops. Get a smaller pen. So here's our water right here. We also refer to this as our aqueous layer. So it is water, that's our aqueous layer. And the first thing we're going to do is, and I'll go ahead and color it in sort of oranges just so we can see the difference. Up on the top, we're going to say that we're going to put in our alcohol. So at first, it looks like one is sitting on top of each other. It looks like we have that oil and water, but underneath, I said it was soluble. Another word for soluble, again, is miscible, which when we get to the lab, which we really will get to, we're going to use capital M to refer to miscible. All right, so from here in the lab, I would ask you to cap this and mix it, or use your glass stir rod to stir it around. I don't have a glass stir rod here, so I'm going to approximate mixing. Pretend my thumb or something or a stopper is over the top, and we're going to mix, 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 mix. There we go. All right, at the end of our mixing, if this is indeed miscible, we see only one thing. So we no longer see two separate layers. Here what we have is the alcohol and water mixed. And I said perfectly mixed because it will become a homogeneous solution if you do perfect mixing just like I did. No, I'm kidding. No, if you stir this up, it will go to a homogeneous solution. So we say that it is perfectly mixed, and that is going to be something that is miscible, which you're going to notate with a capital M on your lab. So any questions about this idea that if it is soluble and it is a liquid, it is going to be miscible? We won't see any difference between the alcohol and the water. And again, the only reason it's blue here is because it has food coloring in it, and that's what you're going to see in the video as well. You'll see some nice blue food coloring to help you see the difference between the layers. So any questions on something that is miscible? Okay. So next up, I'm going to jump all the way to the end, just like we did last time, and we're going to talk about something that is insoluble. So something that is insoluble is also referred to as immiscible. So immiscible, let me go ahead and underline the im here. Immiscible, which you're going to refer to with an I on your lab, that is something that's insoluble. So let's imagine at the bottom, here's our water, again with blue food coloring. And on the top is going to be our alcohol. Set my way for a sec. All right, so water on the bottom, alcohol on the top. And now you're going to mix either with your glass stir rod or, oops, get this going again. There we go. You're going to mix, 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 mix till you can't mix no more. You know, just keep shaking it, and you're shaking it, and you're shaking it, and you're shaking it. And sometimes in the lab, people are like, oh, I've been shaking, and it just won't mix. This is the one that's going to act like oil and water. It is going to completely separate. So you're going to have equal amounts of alcohol and water. So the layer on the top will be equal in size to the layer on the bottom, so long as you add an equal amount of each one. And in the lab, how you would do this is with an eyedropper. So I would have you usually do 10 or 20 drops of each one, and you would count out those drops. So if you see an equal amount of alcohol, an equal amount of water, and there is a definite layer in between them, just like we saw with the oil and water. So let me actually take you back to this image right here. If it is immiscible, it is insoluble, they do not mix. Once they settle out from your shaking, 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 you see a very defined layer in between the two. You can definitely tell that oil has not mixed in with the water. Or in our case, we can tell the alcohol has not mixed in with the water. So any questions on the difference between the immiscible, which means the miscible, which means soluble, and the immiscible, which means insoluble? All right, so now we're going to do that in-between one. So this is what we called slightly soluble before, and here we say it is partially miscible, and you'll be marking it as PM on your lab sheet. So let's start off the same way. So I'm going to have my water down at the bottom. We also refer to this again as our aqueous layer. And then up here will be our alcohol. All right, so you poured in your water, you poured in your alcohol, and you shake, 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 shake. Keep on shaking till your hand feels like it's going to fall off. All right, so if it is partially miscible, it means it's slightly soluble. It means some of the alcohol will go into the water. So what I'm going to do here is I'm going to take away some of that alcohol, and I'm going to put it into the water layer. So some of it's going to dissolve, not all of it, but some of it. Oops. So what we see for something that is partially miscible is we see unequal layers. So even though you put in an equal amount of alcohol and an equal amount of water, now we have in the water, or now it's more properly called an aqueous layer, you have some of the alcohol that has dissolved into it. So again, experimentally, what you'd be looking for in the lab is, again, an unequal volume. So you would see more volume in the water layer and less in the alcohol layer. And just like with the solid, if it is partially miscible, it will always be partially miscible. It will never completely dissolve. So any questions between the difference in miscible, partially miscible, and immiscible? Okay, so we're just about ready for our video, but let's go ahead and take a break. So it is about 6:08 here. Do you guys want to take a 5-minute break or a 10-minute break? I'll probably keep you for about 30 more minutes unless you'd like to stay longer. All right, so I'm hearing a 5-minute break. So let's go ahead and come back at, it's 6:09 now, so let's go ahead and come back at about, 6:15. So let's come back at 6:15 and we're going to watch the video on this and then we'll move on to a couple other parts of the lab.